Um, Good morning, everybody. We're going to have our pretty much our last lecture today. I don't think we're going to need any more after this. Well, there's just a few sections left that we're covering, um, and so yeah, we'll have it. So the last little bits here are on nuclear energy, fission and fusion, and some radiation stuff as well. So, in order to figure out stuff about nuclear energy, we have to figure out where that energy is coming from. And it turns out that uh, when nuclear processes are happening, we end up actually losing a little bit of mass as we go through. And perhaps you remember, way back when we talked about law of conservation of mass, that reactants and products have to have the same mass at the end of the day. It's not quite true. Uh, we're going to see with most chemical reactions, the amount of mass that you do lose over the course of the reaction is really, really quite small. So small enough to be like, a billionth of a gram or something, a nanogram. Tiny, tiny amounts um, that really don't mean anything to us. But with nuclear processes, we're going to see that the amount of mass that we do lose is actually significant, and we're going to see that that mass is going to be responsible for the energy that's coming out using perhaps the one of the more famous equations of science, right? The one that everybody quotes when trying to impress their friends or whatever. So let's take a look at a reaction. When uranium is decaying into thorium and an alpha particle, the actual masses of these, let me write these down. The thorium is 233.9942. And the alpha particle is 4.015. So, if we look at the actual masses of these, we're going to see that we are going to actually lose a little bit of mass from our original 238.0003 atomic mass units to the other side. If we do the math here, we see that we end up losing, where is it? 0.0046 grams. If we convert them into just grams instead, and we are to work with those, remember that atomic mass units, grams per mole, so we know that these reactions occur in equal molar ratios because those are our reaction coefficients, so we can just throw them into grams instead. If we look at, we're losing milligrams level, which is detectable, right? If we're losing micro or nanograms from something, it's going to be very hard to tell. But we're losing actually milligrams here. 4.6 milligrams are lost over the course of 1 mole of this reaction happening. We're going to see that if we hark back to Einstein's relativity, or not relativity, but I guess duality of energy and matter being interchangeable, we're going to see that because of this c squared term, even a small amount of mass loss is going to be substantial. So if we see that the energy that's taking place through this, we're going to see that, this is essentially going to be a delta M change in mass. And so if we substitute that in here, we can see the change in energy would be the change in the mass times c squared. And if we do that, we're going to see we actually need to make this into kilograms. So let's make this. So we have 4.6 times 10 to the negative 3 grams. So 4.6 times 10 to the negative 6 kilograms. Speed of light. I think it's 3.01 actually. Or is it just 3.00? No, it's 3.00. Oh, who cares? Close enough. Bust out the... Oh god, Kevin's already done it. 4.14, okay. Joules per mole. Well, yeah, we're dealing with 1 mole here. So, just so you know, a kilogram meter squared per second squared is a joule. That is just so we are familiar with the SI unit, or the base units there that we can convert into fancier units. That's why we needed this in kilograms. So we get quite a bit of energy out of this. We're talking, that's 414 megajoules of energy per mole of uranium-238 that's just undergoing alpha decay. So we're seeing a ton of energy coming out of this. So we're used to seeing delta H's, for combustion around maybe 3,000 kilojoules per mole, which is 3 megajoules per mole. Compare 3 megajoules to 414 megajoules. So we're going to see that this is going to be an extremely energetic process. And so it kind of makes sense that we would want to see if we can't harvest these as potential energy sources, which we do. But first we have to do a little bit of theory going into this sort of thing before we talk about fission and fusion. So this kind of phenomenon is what's called the mass defect. Let's write that in, how about light blue? So the amount of mass that we lose over the course of a nuclear reaction is called the mass defect. And again, it's far more substantial than something you'd see in a typical chemical reaction. Oh, creature, relax. Alrighty. And so we're going to see that this amount of energy that's released is going to be essentially the same energy that it would take to put these things back together again. And we're going to see that the opposite of this is going to be called binding energy, or specifically nuclear binding energy. And that's going to be the amount of energy to essentially kind of recombine these things, to combine nucleons into a nucleus. So nucleons, neutrons, and protons, if we were to just take them all and glob them together, it's going to take energy to do that. And we're going to see also that the mass of all those nucleons that we would put together is not the same as the mass of the nucleus itself. Doesn't make sense, right? Because this is nuclear chemistry. You don't have to worry about that, where there is that mass defect, right? So it turns out that once you have the neutrons interacting with the protons in there, you end up actually decreasing their mass. So your mass of your nucleus is a little bit less than the mass of your nucleons that you put together. So as a result, there is that mass defect there. So anyways, suffice it to say that the binding energy is going to be the amount of energy that's needed to put all those nucleons together into a nucleus. Kind of the simplest example of that would be to take some protons and neutrons. Let's take a couple of neutrons plus a couple of protons and make a helium nucleus. There is some energy associated with doing that. Actually, no, this is the opposite. The energy goes on the other side. I lied. So, because there is energy that's needed to combine these, it's going to come out if we separate them. That's kind of what I'm trying to say here. So if we give it more energy, we can split this guy up into neutrons and protons. And so that's going to be kind of the energy to overcome that binding energy, right? So we're going to need to overcome that if we want to break our nucleus up into these nucleons here. And so if we were to just look at a couple of values here, that's the binding energy. It's going to be actually pretty varied. There is a graph of nuclei and binding energy. We kind of skyrocket up, and then we decay slowly as we go through here. If we look at our atomic mass as we go through, or just specifically isotopes, we're going to see that this little dot here is helium. And we're going to see that our maximum is going to be iron 56, if I remember correctly. And way out here, of course, we have our uranium. Let's say 235 or 238. Doesn't really matter. They're about the same. Yeah, its peak is iron. So iron is actually the most stable nucleus of all of ours. So it has the highest binding energy per nucleon, which is typically how these are established. And so we're going to see that as a result, because has the highest binding energy, that means if we take nuclei and make them kind of get closer to iron, we can get energy out by doing that, as we make these nuclei more and more similar to iron. So that means for us, taking nuclei that are small, putting them together, we can kind of get them to get closer to iron. Or on the other side, if we take really big atoms and break them apart, we can get them closer to iron by making them smaller. So during this process, we can actually get energy out. And so, do I want to look at this anymore? If you want numbers on this, I guess I have numbers here for your reference. For the binding energy per nucleon, this is not something that we're going to... Did I give you any problems on this? Maybe. Anyways, the binding energy for this one per nucleon is going to be, for uranium, it's 1.21. Let's make this 238 then. For uranium, it's 1.4 joules. Oh, sorry, times 10 to the negative 12. And for helium, it's going to be 1 point something. Let's look it up. 1.13. So these numbers do come from that same mass defect equation, but just divided per nucleon. So, for example, in iron 56, you have 56 nucleons, right? That's your mass number. For the uranium 238, you have 238 nucleons. So you look at your mass defect for breaking those up into nucleons versus the actual nucleus itself. And you would use your E equals mc squared equation. You get some joules out, divide it by the number of nucleons, and you would end up getting this here. So, cool stuff. And so this is just for to like essentially assemble the nucleus out of protons and neutrons. So it's not a real process for us, because nobody's going to take 92 protons and 146 neutrons and stick them together, right, to figure out the binding energy of the uranium. These are all more just mass-based things. So we know the mass of a proton and a neutron. We know the mass of a uranium-238 nucleus. So we can see the mass difference there, and just use this kind of as a theoretical number. So, exciting stuff. But the point is, we can take big things and break them apart, or we can take small things and put them together. And as a result, we're going to have two processes out of here that we're going to talk about. So, process 1 is fission. So fission is breaking. We're going to break nuclei apart. Standard example for that is uranium-235 plus a proton. And we're going to see that once this happens, you end up with uranium-236, which is terribly unstable. So much so that it immediately will break down into various daughter nuclides, or just fission products, sometimes they're called. We're going to see that this could break down in any number of ways, but there are some important components here. If this breaks down, one such example, you get tellurium and zirconium out, plus 2 neutrons. This isn't to necessarily say excited state, but it's unstable. So uranium-236 is not a stable isotope. So shoving that proton in, uranium-235 kind of stable, relatively so. It's got a long half-life. However, you throw a neutron at it, and now you have a very, very short-lived species that's going to be able to spit out a bunch of energy as it breaks. Because notice that these nuclei are closer to iron-56 than uranium was. Uranium-235 is way far away from iron. But these nuclei, the daughter nuclei that come out, or fission products, are closer. And so as a result, if we kind of look at the graph here, they're going to have higher binding energy, which means that we have to have gotten some energy out as we've made them. Because if it would take more energy to make these nuclei, we can get that energy out from breaking a larger nucleus. All right. Another way it could decompose would be into barium and krypton. Yeah, that's a common one. But this time we have 3 neutrons. So these would be examples of fission. Again, notice these 2 daughter nuclei are closer to iron than the uranium was, meaning that this process is going to spit out a bunch of energy. So we'll be able to harness that energy. But what's more important, though, is that notice with both of these, we end up getting some neutrons out of here. And so, in order for a material to be what we call fissile, that means you can have it perform fission, it must produce neutrons when breaking down, and the energy kind of from the added neutron it must overcome the binding energy of the original nucleus. So, who cares about this whole paragraph? Suffice it to say there's really only three fissile products that we really deal with. So uranium-235 is one of them. What else do we have? They're here somewhere. Plutonium and other uranium. So there's really only three nuclei that we're going to consider that will readily undergo fission that is going to be energetically favorable. So if you try to spit a neutron at uranium-238, for example, even though it's more common, when we absorb it, the binding energy is not going to be enough to kind of overcome the energy that it would kind of take to absorb that neutron and split apart. So it's just not enough. So the you have to either just completely destroy it with this super fast neutron, which is kind of not energetically favorable because you're going to have to then figure out some way to get that neutron really fast, and that's hard to do because neutrons are not charged. We can accelerate charged things, but it's very hard to accelerate non-charged things. So kind of doesn't really make sense. So there's kind of three main nuclei that are readily able to undergo fission when we throw neutrons at them. Notice that because we're producing also more than one neutron, the fission is self-sustaining. And we have that kind of classic graph here. Here's our uranium. We're going to throw a neutron at it. It's going to break apart, producing 2 more neutrons, or 3 more neutrons, let's say. Those 2 neutrons, or 3 neutrons, depending, can go hit other uraniums, which can then go and hit other uraniums, the neutrons that spit out. And as you can see, this process will grow exponentially as we keep spitting out neutrons. So we see we keep spitting out more and more neutrons. And we call this a chain reaction, as this exponentially occurs faster and faster as more and more neutrons are produced. That's calling it a chain reaction. And we're going to see that there's some vocabulary terms here. We're going to see the amount of fissile material necessary for a chain reaction is called the critical mass. And the critical mass actually is not a constant because it depends on kind of where your substance is and its shape. So if you have your uranium-235 in such a shape and container that neutrons that are coming out are sent back in, you can actually have a smaller critical mass. But if you just have it kind of just sitting there and the neutrons are just going out, then you need a larger critical mass to achieve your chain reaction. So we're not looking at a constant value here. It is a little bit dependent on shape. And unfortunately, things will happen kind of immediately as soon as you have critical mass. And so this is how the nuclear bombs were made, is that they would you'd have your bomb here, which is essentially just a tube. You have... they would make them such that you had kind of shapes of uranium. Here's your bomb as it goes down. You'd have some sort of chemical propellant here, so that as it hits, it will knock that uranium. These would be both subcritical, by the way. So smaller than the critical mass, so they can't undergo a chain reaction. But as soon as they're shoved together, so after your bomb kind of detonates, now you have a supercritical mass which undergoes this chain reaction, and kaboom, there goes your bomb. So you just have some sort of propellant to shove that other subcritical mass into your top subcritical mass, and now you have a supercritical mass which undergoes its chain reaction, and there you go, you have neutrons all over the place causing more and more and more, and you have your nuclear explosion. By the way, uranium-235 is about 0.7% of uranium. Most of it is 238. And so often you'll have to need to enrich it. You'll need to enrich it to about 3 to 5% uranium, which is what we notice other countries doing, I suppose. So if you are noticing countries are enriching uranium, sometimes that's a bad thing. So if it's used for energy, that's great. If it's used for bombs, that's not so great, right? We do not want to do that. Yes, and of course Kevin has the answer, right? You make it into a gas. So fluorine, pretty much we'll just deal with its one isotope, the 19 fluorine. But if we remember from effusion rates and Graham's law, uranium-235 will effuse more quickly than uranium-238 will. And so you can kind of separate it out along the tube. So here goes your uraniums. And your uranium-235 will go a little bit farther as a gas. And so you'll be able to kind of isolate it and make it a little bit more concentrated within your sample. And so that's how you will enrich uranium. I probably should not label this video as how to enrich uranium, because I'm sure that will probably violate some sort of YouTube policy. So, but there we go. That's how it's technically enriched. But that's neither here nor there. And neither is the how to make bombs. The point is, though, the energy that comes out of fission can be used to make electricity. There's a couple pages in the book on how reactors are built and the different types of reactors. We're not going to worry about that. So if you are interested in how nuclear power plants work, that's in there. Essentially, the energy that is released by these nuclei is used to boil a liquid, usually water or deuterium, deuterated water, and you can essentially turn it into steam to push a turbine and then recondense it and then boil it back up again over and over and over. So it's just there to push a turbine using magnetism to generate electricity. But we end up getting quite a lot of energy out, so it's very efficient to boil that water that you're doing there. And of course there are problems because the nuclei that you get out oftentimes are far more radioactive than the uranium that you put in. And so nuclear disposal is a whole other issue. But we're not going to worry about that here. All right. The other way to get energy out is fusion of small nuclei. That's the ideal way. This is what happens in stars. Typically, you need about 40 million Kelvin to get this to work. Because you're going to be shooting nuclei at each other. So with fission, you're throwing a neutron at a nucleus. A neutron is attracted to a nucleus because there's not charges to worry about or all that. And so there's not only a little bit of gravitational attraction, but you have some strong nuclear attraction as well. You need this because nuclei, they're positively charged, right? So if you want two nuclei to combine together, we have to have them moving so fast such that they can overcome their electrostatic repulsion. So not a problem with fission because neutrons are neutral, but because these are nuclei are positively charged, trying to put two nuclei together gets very tough. And as you can imagine, as nuclei get bigger and bigger, you have more and more positive charges, even harder to squish those together. But even so, if you look at the binding energies, we have our smallest binding energies with things like hydrogen. So it's kind of not only advantageous because you're going to get a lot of energy out, but you also don't need to have them moving as fast because they're going to be kind of the minimal charge that we have, just positive and positive, right? So let's see here. You have a whole bunch of different ways to make fusion products. Very often what you're seeing in stars is that you have all sorts of potential products. You can have tritium and hydrogen coming together. You can have all sorts of fun stuff here happening. These would be examples of fusion reactions. We are taking nuclei and squishing them together. You end up getting actually quite a bit more energy out than you do from fusion because of that binding energy difference. So for hydrogen, the binding energy is really, really small. So as a result, you're going to end up getting quite a bit of energy out when you fuse hydrogens together to make helium. This is what happens in stars. That's why we have that wonderful energy source in our sky just blasting us with energy all the time. That energy all comes from fusion of these nuclei. So again, making them closer to iron. 56. That's a 2. No. 56. So again, we're getting closer to that highest binding energy, the most stable nucleus. Unfortunately, in order to get this to work, 40 million Kelvin, that's a very, very high temperature, yes? In stars, when this is happening, you're looking at 100 million Kelvin. Not really something that we can deal with in the core of a star, right? We can make those temperatures on Earth using magnetic fields, but it's extremely energy inefficient to do so. And so, unfortunately, right now, although there's always, hope for this to work, the energy that we need to make things so hot and to have materials that can withstand those temperatures, which they can't, which is why we need magnetic fields instead, which are not really tangible. It just energetically, it costs more energy to get those temperatures than you get energy out from actually doing the fusion. So there's a net energy loss that's kind of not useful to us, right? So unfortunately, fusion is not an energy source we can do yet. However, we can do that in bombs. We can make thermonuclear bombs, hydrogen bombs as they're called, which do end up having quite a bit more kind of explosive power than fission-based bombs. So unfortunately, all we can do is make bombs with these. So sad things. So kind of right now, not energetically, or not feasible, even though we do get quite a bit more energy out. Simply because the temperatures that we need are just not achievable or sustainable. So sad times. We cannot basically make fake stars on our planet right now. So with that, enough of fission and fusion. Let's talk about radiation. Radiation and safety with dealing with these. So let's talk about our kind of 3 particles. we're going to see that alpha particles do have the most energy, but because they are large, they can't really get into our bodies. The skin will block them. Because shooting a nucleus at our skin, which is made of atoms which have nuclei, positive charges repel each other, so the alpha particles don't really get into our bodies. Beta particles can go about a centimeter into your body, and gamma are completely penetrating because those are just light rays. And so if you're thinking of outside sources of radiation, of course gamma would be the worst one for us, right? And alpha is harmless essentially from the outside, though of course alpha particles don't just come, every nuclear process will come out with gamma as well. It's just how much gamma and what wavelengths you're looking at there. We're going to see that many types of radiation are ionizing. So that means they are low enough or high enough energy to overcome ionization energy. So remember, ionization energy is the energy to remove an electron. If you give an electron enough energy through a photon, it might be able to leave your atom entirely. So remember, you can keep promoting electrons to higher energy levels. Eventually, if you give it enough energy, it's just going to leave. And that's ionization, remember? So if it's high enough energy, it's called ionizing radiation because it can overcome this ionization energy, producing ions in your body. If you have that, so if you take a water molecule, remember we're 70% water, so if we are going to be hit with radiation that is ionizing, the most likely target is going to be a water molecule because, again, that's most of what we are. So you end up getting a positively charged water molecule out, plus an electron. We've ionized that water. Yes, and you can have all sorts of dimers happening. So thymine, you've got conjugation in there that can be broken apart with UV. That can cause radicals, and radicals like to react with things. But technically, that's not ionizing radiation because you're forming radicals. Ionization energy is what we're talking about specifically with ionizing radiation. Not to say that that energy couldn't be ionizing, but that particular process does not form ions. That's just forming free radicals. Speaking of free radicals, once this positive water sees another water, we can undergo our proton transfer, and we get out a very, very nasty thing indeed. This guy is a hydroxyl radical. Wow, loud planes outside as always. This little thing in the environment is quite nice because it is essentially the vacuum cleaner of the atmosphere. It will destroy all the kind of bad stuff that we have. So all those chlorine radicals and all that stuff can be neutralized with hydroxyl radicals. But in the human body, these things are extremely reactive, and they will go and rip an electron off anything they can to become hydroxide. So they will try and get this because unfilled octets, as we know, are not stable. We want them to be filled. So it will do everything it can to try and steal these electrons. So it can steal it from a DNA molecule, a protein, a cell membrane, wherever it happens to be around. It is happy to steal electrons off of other things, which cause them to then break down or start stealing electrons from other things as well. And we end up with a whole disaster of things happening. Not from fluoride, I doubt. I doubt it. Because fluoride would already be supercharged there. So you need to look at the electrochemistry associated with this. I'm pretty sure that the cell potential for this would be less than the cell potential for reduction of fluorine. So I doubt it. That being said, fluorine, if you were to try and make that, you would you're essentially making a fluorine radical, which would be even more reactive, right? So I don't think this would happen. I think you're going to end up having the reverse reaction be much more favorable. If you want, we can look up the cell potential found a K value for this process, but my guess is it would not be favorable. So you would probably not be able to take it off effectively. So, I mean, an individual fluorine atom is so reactive. Just difluorine by itself is already so reactive. Imagine it not paired off. Forget it. So, probably. I doubt it would. I don't think it's going to happen, though. Anyways, so the point of all this is big damage. You really wreck your molecules with this. So radiation can make you very, very sick because it's messing with all sorts of functions that your cells need to be doing normally. Of course, we do have things called antioxidants in our body that exist solely to neutralize things like this, but it's just kind of a probability, right, of how quickly that antioxidant will be able to find this free radical and neutralize it before it starts doing all its damage. So, vitamin C, vitamin E, all of our antioxidant vitamins that we have that are kind of sacrificial reducing agents, oxidizing agents, reducing agents, oxidizing agents. They become oxidized, so they are reducing agents. My bad. They are sacrificial reducing agents to prevent other things in your body from being oxidized. Yeah, these are going to be stealing. Yeah. So, I'm sorry. They are oxidizing agents. No. They are reducing agents because they're preventing other things from getting oxidized. That's right. Okay. Cool. They are going to be oxidized themselves such that other things don't get oxidized. So they are reducing agents. So vitamin C, vitamin E, very important for us. We have other antioxidants as well. And we have enzymes to kind of deal with things like this, but these can cause big damage. And so radiation is a problem. And so we have a couple of units for dealing with radiation. We have the rad, which is this per kilogram of tissue? Yes, it is. So a rad is 0.01 joules of radiation per kilogram of tissue. We have the gray, which is 1 joule per kilogram of tissue. But these units don't take into account that different radiation affects things differently. So we've talked about alpha and beta not being so bad from outside your body, but if you have consumed something like radon that is an alpha emitter, that could actually cause a ton of damage if it's already inside your body. Because think now, that alpha particle can't get out. It's just going to start wrecking things as it goes through. It can't be deflected away so easily. It's just going to be bounced around And as it does so, it's transferring energy to wherever it hits, and so it can cause a lot of damage. And so alpha particles are actually probably 10 times as bad. Alpha particles are roughly 10 times as harmful as beta or gamma particles are inside our body. We call this thing the MBE, CBE. I have it written down. Let's see. RBE, of course. This is the stands for relative biological effectiveness. Biological. Nope, let's try that again. Biological effectiveness. So alpha particles, which are much more harmful to us, have a high RBE, roughly around 10 or so. And beta and gamma have RBEs of roughly 1. If we incorporate this kind of factor into our units here, if we take the number of rads times your RBE, you get REMS. And so it's just there to kind of standardize the fact that different types of radiation can cause more harm than others. And so REMS, or more commonly millirems, are what we're used to seeing, are another unit of energy. So they just incorporate this harmfulness component into them. So we're going to see that that's a unit that we use as well. Just so you know, if you want to think of how much we get exposed to, the book has a handy chart. Radon is our most common exposure to radioactivity, naturally occurring. Remember, it comes from uranium's decay process. Unfortunately, as a gas, it comes out and can do all sorts of horrible things. You get about 200 millirems of that a year, just annually. And if you were to, be a normal human getting, X-rays every so often, X-rays account for, from medicine, or dentistry, that's about 40 millirems per year. So you don't have to worry necessarily about going to get medical X-rays. Of course, you don't want to be getting them all the time. Like, that would obviously not be good. But just comparing to how much you get from fluorine, and actually this is about the same amount that you're going to get from just from rocks and sunlight. Give you a little bit more than 40, but it's about the same that you just get from rocks and the sun. So we're going to see these are not nearly as problematic as radon is. So again, very important that if you are going to be moving somewhere, buying a house or something, that you do check that radon report, because you want to make sure that you're not getting extra radon, because that is our biggest kind of pain in the ass to deal with for radiation. This is for normal humans. If you're an X-ray tech, probably you're going to be exposed to more than 40 millirems per year. Though obviously you will do your best to protect yourself by going into other rooms and having lead shields and all that stuff. Lead shields work, by the way, because lead is such a dense atom. You blast it with X-rays. It has so many electrons, it's happy to ionize itself, kind of a sacrificial ionization source for you. So when you get your X-rays done on your teeth, you have your lead shield on your chest and the rest of your body. That lead is there to absorb any stray X-rays, because lead is a very good absorber of those, because it has so many electrons that all have different energy levels, and so the chance that one of those electrons can absorb that energy is very high. So that's why you use lead shields. But suffice it to say, there we go. There's kind of your radiation dose. dosage-ish there. All right. So that's it for us. Thankfully, all this stuff that we've done today and maybe even last time is more for your homework. If you've taken the practice exam, you'll see that the questions are just on like what's an alpha particle, or maybe not that obvious, but like, you know, what's the product missing from this nuclear reaction or something? You know, is this an alpha particle or a beta particle? You know, so it's simpler stuff. So this stuff is more for your homework, and once you do that, then you can dump it out of your brain. The nuclear questions on your practice exam will be the similar difficulty and kind of topic as the ones on your real exam will be. So, with that being said, the only kind of request for review I've got is from Kevin. So we'll do some generic review. Probably what we'll end up doing is we'll take a look at some of the problems from the practice exam and do those. And so we'll take a look at those, and we'll spend some time looking at them, explaining them. Just because that'll be kind of more focused on the topics that the real exam will have within those chapters. So probably let's do that on Wednesday. So tomorrow is your day off. Do your homework. We'll have Wednesday as our review day. If, as you guys are doing stuff, and you come across a lot of questions on the practice exam, and you come up with more, we can do another review on Thursday if necessary. So we'll see, but try and put questions sooner rather than later, just to make sure that we can get as much into Wednesday as possible, so that we can spend at least an hour doing that. So, but yeah, that's it. So you have survived 113. Things are going hopefully not too bad. Your practice exam is up, 60 questions, 95 minutes. So still roughly that 1.5 minutes per question. It again will have the breadth of topics and the difficulty of questions that you're going to expect to see on your real exam. So you can take it as many times as you like, but it is timed so you can get the real experience for getting used to that fast pace. There is also the formula sheet and periodic table that is provided with the ACS exam that is given to you as well as a separate file, so I suggest you print that out or otherwise have it handy, because it's going to have all the equations you're going to need, and it's going to have all of the periodic table information that you're going to need as well. So just kind of make sure you're fully prepared for that. Have your calculator, have everything ready. We want everything to go as smoothly as possible, right? So, it may be worth it to take it, today or tomorrow, and then maybe take it again on Saturday or Sunday, just to, practice, right? The more you can do, the better you're going to do on the real exam. Remember, you're not going to be expected to get very high scores. So it is very fast paced, and it is again designed so that the median score will be half, 50%. So don't think your morale is going to be destroyed by that. So just accept that. So it's meant to not be easy. So that's the purpose of it. So that's there. Let's see. Do I have any other announcements to do? Just so we're very clear, your final is opens on Monday, 5/10 at 12 a.m. Closes 5/11 at 11:59 p.m. So you have 48 hours to take it. Again, you're going to want to set aside 95 minutes, maybe a little more, just so you can get yourself comfortable and relaxed and everything. You'll have 60 questions, 95 minutes, and it's a multiple choice exam with 4 options. So no E as your answer. So Just guessing you can get 25%. Hooray. Maybe, if you're lucky. But hopefully that's not a grade you're shooting for. So it is multiple choice, four potential answers. We're going again from chapters 13 in our book to 22, except chapter 18. So, what is chapter 22? Is that... No. Chapter 21 is where we end. Yeah, not chapter 22. So, everything we've covered this semester, except for environmental chemistry, non-metal chemistry, and transition metal chemistry, that will be on your exam. So everything else, those other 3 chapters, forget about them. At least once you finish your homework on them, then you can forget about them. So you don't need to worry about those. All right. Any questions on that? Excuse me. Alrighty. Well, it has been fun, I suppose. I've had to relearn a lot of this material that I have not looked at for 5 years. So that's always fun. And I guess it had been 5 years since I took the class, since I actually taught it. Actually, more like 8 years. So it's my 3rd time seeing this material after 13 years. So isn't that nice? So I do want to say Kevin probably knows more about this stuff than I do, but we'll see. So with that, it's our last day of real class. We'll have a review on Wednesday, maybe a review on Thursday. And that's it. So it's been fun. I'll probably see a bunch of you for organic in the fall. We'll see, Kevin. Stuff is annoying. So, well, some of it's fun. Some of it I like. I like electrochemistry. I think that's awesome. But kinetics, yeah, I'll see you guys in the fall then for OChem. It's going to be online again, same as it is now. Although we are talking about potentially having a couple of safely done lab sessions for people who can make it to campus. I don't know how this is going to work because obviously there are some of you who are taking it from Bakersfield or Porterville or other areas, and so it would be kind of an undue burden to force you to come to Ridgecrest just for that. So we'll see how that's going to work. It would be nice to do a real lab, but that may need to wait until the fall or spring. But again, spring may be online as well because it is a sequence class. And so, it would be kind of awful for it to be like, okay, here's the first half of the sequence online where you can take it from Bakersfield or whatever. But then in the spring, when it's kind of like, now you have to come to campus, we'll see. I don't know how it's going to work. So maybe what we'll do is it might be hybrid. I don't know. We'll see. So I unfortunately do not know that far yet. I do know that fall is online, so it'll be just like this. We'll have our lab simulations. We'll see what we can do. So, alrighty. Well, in that case, enjoy the rest of your Monday. Enjoy your Tuesday as well. I'll see you Wednesday for review, maybe Thursday for review. And then I will listen to your tiers on Monday and Tuesday. And then we'll go from there. So, awesome. Okay. See you guys.